Welcome back to the Semiconductors chip design series number 11. Today we talk about the technology of testing. The testing is not a trivial matter in the semiconductors. Every semiconductor company has a good number of testing engineer, and we talk about what the testing engineer will do. For example, when wafer is completed by a semiconductor process, it has many dies on it, and what we do first is to bring it to the test station, and test station is like the Japanese test station is pretty good. Teledyne has test station. Basically needle come down to the bonding pad, so you have a bonding pad around each chip, and needle come down to each location, and using this needle the input pin get some logic level low or high, and the output goes to the monitor. It goes high or low, and tri-state is going to be tri-state if necessary, or sometimes high or low. It sometimes work as an input and output. So this station provides this needle touch down to the one chip on the die, and this large computer system and the monitor, and the test engineers run basic test. And this test, what kind of test we talk about that today? When chip pass the test, then drop the color die on this chip, and good chip, and this is bad, there's no color die. So what happens is you bring it to the next stage. Silicon wafer is crystal, very brittle, like a glass. So this die, using a diamond cutter, scribed into each chip, and the robotic hand come and using vacuum suction the good chip, pick it up and put it in tray. So good chip all has a color die, and this tray is going to be processed for further testing. So this robotic chip scan each column or row and pick up all the good chip which has a color marking on it. So this tray is going to have a good chip and processed to the next level. And usually chip is mounted in the substrate and bonding is performed. But if it's nowadays there is a technology to put those chips on silicon itself, so it's going to be sub-silicon and put the chip, multiple chip, this upside down, and all interconnection done on this silicon, and put the larger substrate and do the bonding here like that. Okay, and if it's each die is included in one substrate, this IC chip, then it's bring it to further testing. So IC chip is going to go into the test machine and test it and come out, and the further testing reject the bad one. So what happened is this kind of needle, you can test the DC level of the signal and functionality, logic level, but it's impossible to check the AC. So AC is usually after mounted, AC is checked here. Okay. So this kind of module, multi-chip module, this AC test is not done, impossible until you make a substrate, the ceramic, and it's going to be pretty much by design. You hope it works. After it's substrate mounted, you do the various testing, and mostly AC. Make sure that, for example, clock frequency is applied, a little bit lower frequency applied. Make sure it's working and increase to higher level, and still works. If somewhere when you increase the higher level clock, it stops working, then it has a problem on the speed. Okay, so that's the whole process. The question is, what kind of test we need to perform here on wafer. And after it's become packaged, after package, test after package. If this chip include memory, then the memory has to be tested. Its memory and the logic is going to have two different kind of test. And let's talk about that memory. It's like a dynamic memory or random access, RAM, or static RAM. This memory testing is like, there's not much you can do except for the basic stuff, like you have a big memory space, you write 1 and read it, and you write 0, then whole becomes 0, and read it again. You do opposite, whole memory contain 1, and you write a 0, and you read it and rewrite the 1, make sure it's turned into 1. This is to check stuck problem. So what happened is the silicon wafer, the transistor, sometimes has a defect silicon, and this defect silicon pulling memory output is a low or high all the time. So if you read and write, you can detect this, and you have to repeat this multiple times because sometimes it has an intermittent problem. Intermittent problem is this silicon defect cause is stuck to low, but this stacking is not that strong. Sometimes it works, it's high, but if you try 3 times, you write 3 times and read it, it sometimes works, sometimes it doesn't work, that kind of issue. So you have to repeat this. And another one, typical one, is a checkerboard pattern, 1 0 1 0 and 0 1 0 1, so and so. And checkerboard is the opposite checkerboard. And write a checkerboard and read it, and checkerboard and write it. This is to check C in the, there is a common driver in the memory. Driver is common for entire row, and check this interaction between 2 bits. When this write 1, this write 0, there may be some bad interference, and flip this to 0 when you write 0 right next to it. So checker pattern is checkerboard pattern. And of course you have to do random pattern. And how much you do random pattern, more is better, but there is a limit. You can't keep doing a memory test. So it's almost impossible to check every different cases, because say if you have a 1 gig memory, 1 gigabyte, and that means 8,000 million bit. So 2 to the 8 gig, that many different patterns possible, and possible it's impossible to generate all the patterns and test all the patterns. So somehow this random pattern, we hope it's hit if there is any defect, and we go work with the probability, and we talk about this later. It's called the AQL levels. AQL is a QA, quality assurance department. Hire a lot of test engineers, work on the AQL level, and this is the part of the chip. Sometimes memory is included in chip. This is the memory area, and usually have access by data bus and address, so you can do read and write on this part of the memory. And if architecture doesn't have it, probably at the design stage it should provide for testing purpose this memory access from outside. So that means there is an external additional pin which architect doesn't need but necessary for testing. So testing purpose IO pin has to be created. Okay, now logic part. How you test the logic part? The logic part is another very tricky one. For example, this kind of logic, you have selector, right? So when this is high, this guy is selected, D1, and this D2. So Q is going to be D1. This is low, then Q is going to be D2. This is selector, right? Okay. Now suppose there is a silicon defect and this guy is stuck to say high, always selecting. Okay, but as long as D1 and D2 is same, you don't see it on the output, right? And you can deselect this guy, no problem. And only when you deselect this one, so deselect D2 and D1 is high. That's the only time you see this defect show up on the output. So that means the logic, you don't see the output, the effect of defect, not all the time. It's if you have a random logic here, logic design, and you give all kind of pattern, logic input pattern, but you don't see every possible combination here. So you monitor output and all the test pattern generate this output, and test seem to be fine, but there is some percentage of cases you're not testing. And when you have 1 trillion gate, the percentage of cases that not tested, this typically this method, test pattern and output, monitor output pattern, can go only less than 50%, I would say, for the LSI chip. 1 trillion gate, you probably test only in the good test patterns 50% of the gate functionality. It's impossible to test all the gate functionality. And we're not talking about the bug. The bug is assumed it's completely debugged by the design, logic design. Okay? So what's happened is the test engineer first generate the test pattern. And usually functionality. So you test out, you have a logic design, and you have input and some of the tri-state and output, and they all hooked up with the test machine computers, and computers output monitors, input generate kind of things. Functionality, you look at the data sheet, and every function written in the database data sheet, you create that functionality. And this is not that easy either, because when you say A plus B in the CPU, what test pattern do you give? How about 0 and all 1 and 0 and some random number? And in the simulation using logic design, generate this pattern. So you bring the register values and you do the execute add instruction and check the output, and this should be random plus random 2, and this should be all 1. They should be all 1. Those test pattern, the using simulation, logic design simulation, you generate this test pattern and load this test pattern into this one. And for example, like exception flag, right? When you add a number and overflow exception flag raised. And once flag is raised, what happened in the hardware? And it's depend on the CPU design. And nowadays CPU is more complicated. For example, there is a CPU. One time it became popular, like I think over 10 years ago, so-called speculative. Branch instruction. And what it is like you have a, if register 1 is 0, then you do something, right? Okay. And the speculative branch instruction is, you know, this repeat many times until R1 becomes 0. So you repeat, say 1000 times, and R1 suddenly becomes 0, then branch out. So when you do this test, you monitor this register if it's 0 or not, and that's waste time. So in order to save time, CPU assume this is 0 and execute the next instructions. But when it's become 0, then CPU already execute this much, and this much the register value changed, right? we have to correct it. We have to roll back the CPU's task, and it's happened once every 1000. So it's okay. It's still, you speed up a lot the CPU speed. That's called a speculative branch instruction. And this kind of things complicate the hardware, because once this happens, then on the CPU, the hardware go back and roll back the instruction and the corrected registers. Okay, you cannot change the cache during this instruction. If cache is updated, there's no way you can go back and change the cache back to the original value. But some register value, you can correct it. So after changing register value, you go back. So this has state machine in the CPU. How do you test this kind of cases? This is the big headache. How can you test it? You write this in a simulation and give this program to simulation, and simulation generate a test pattern, and test pattern you load it up and test it. You can test some cases, but not all the cases. It's so many different cases happen. So again, probably we're talking about how many percent of logic is tested. And you know, it's not only silicon defect. Like FPGA, you cut the fuse on the silicon chip, and you don't know if fuse is properly cut, or maybe some remaining still connected. You never know. But if you have so many gates, you cannot tell unless you do the correct testing, and maybe sometimes that's impossible to test the certain cases. Okay, and why impossible? Because chip has a lot of register or flip-flop inside, and those are the problem, because you cannot set arbitrary value in these internal memory element. So if logic depend on this output of flip-flop and output of registers and stuff, then you have to figure out how to change those contents first, then use that result. But their logical relationship probably may prevent you from setting up those values in a certain way. So it's a really difficult problem. There are some method some company use. That means every flip-flop on the chip using a shift register and all connected in a single chain. And this is flip-flop in and the flip-flop out. So if you do that, you can set any value inside the flip-flop, like exception flag, whatever you want. Then you can test more cases, but still it's impossible to test 100%. This significantly increases the coverage of test. Coverage of testing. It's lucky if you go up to 60%. And when you have a 1 trillion gate, wow, that's pretty bad, right? So we talk about, say, when you make a PCB board, this is typically the example used. you have one parts, let's say 1,000 parts on the PCB board. Okay, one part defect rate is 0.1%. And as you know, in order to be good PCB board, every part has to be good, right? So each part, the chance probability of good parts is 0.999. Okay, but if you have 1,000, probability of all of them is good, it's going to be 0.999 1,000, and this is going to be like a 35. So 35%, only 35% of PC board you assemble is going to be good. Remaining is scrap. Okay. So this seems to be very good. If you translate it into the silicon, say chip may have a silicon defect here, and this chance of having silicon defect may pull the one logic low or high. Okay, this chance is 0.999. Then if you have how many transistor, 1 million transistor, this is guaranteed 100% is bad chip, right? It cannot be this level. It has to be 99999. This level of probability of having a good transistor on chip. Otherwise, so this is yield, right? And AQL level is something like, if you do sampling and it shows 1% or less defect, then AQL level is 1%. The any lot, if you take the sampling and the 1% is more than 1% of bad, then it's rejected, this entire lot, and go to the screening. Screening means test every part and get the bad parts out. So this is a traditional AQL work. The quality assurance engineers has been doing that for many years. Okay, why sampling? Depend on product. Some product is, for example, like this iron rod supposed to hold certain load, right? Then you cannot test 100% because this is destructive test. It's break. Then when it's break, you see the breaking point. Then you know it's satisfied the requirement or failed. And if you do every one of them, for example, the this armor, right, is made for the military. You cannot test 100%. You shoot everyone and they say, oh yeah, 99% is good. Then there's no more. So you take a sampling. The sampling can tell only the chance of being really less than 1%. Even sampling shows less than 1%. In the actual lot may have 2% defect, right? So same thing apply to the silicon chip. The function test, you test only 60%. So this is a sampling. You count on sampling. 60% is good, all good. The chance of having a bad chip here, how many percent is going to be? When you have a 1 trillion gate, this chance is going to be very high. The sampling is not enough. You have to increase this to 90% test and say, yeah, 90% of time gates all tested. 90% of the gates working fine. Only 10% is not tested. We don't know if good or not. Then it's pretty. It's get closer to the kind of, satisfactory quality by testing. This is test engineers' job. How to increase the coverage of testing, and this is a very difficult problem to solve, scientific problem to solve, when you have many gate and many flip-flop inside, and random logic from outside, inside the box. Is there any defect? That's a question. Well, yeah, I tested many patterns. So what is the coverage of testing? Okay, so test engineering is not trivial. It's very difficult, facing a very difficult problem, and especially nowadays they're going to mount a module on the silicon. Okay, so no additional test is done. You do the test on the wafer, and that's all you have. And this test is going to be actually done very quick, because computer load up the test pattern and run through it. If there is a output, monitoring output and mismatch, then it's a bad die. Die is one of chip on the wafer. And if it's a good die, you put the color, you drop the color die, and it's picked up as a good chip. How many percent you can cover is a very difficult issue in the test engineering. But testing itself, no matter how big the test pattern is, it can be done very quick, because computer load it up and run through it. So it won't take few seconds for each testing. The question is how to generate this test pattern, and this is the problem not solved when the industry is going to bigger and bigger chip, and some of chip they use the entire 12-inch wafer as a single chip in the AI, and talking about some trillions gates. It's going to be very difficult, and it's provide the way to access each section of wafer for testing, and has some, like a dynamic RAM, has spare modules around. If they find a defect part, they reroute it, use a spare in order to save the entire wafer. Otherwise, yield is going to be 0. Okay, I hope you had an interesting discussion here, and we continue the semiconductor technology in the next video. Please subscribe and click like. Thanks.